Hey everyone, I'm having a massive technology failure today, so we're going to try to get by with barely readable screen here. Today I want to talk about binary trees and how to represent them. I was going to have some code to put up for this, but I don't, so what I will do is simply draw for you what the binary tree data structure looks like. We're going to have a class of binary trees that's made up of a binary tree node object and a binary tree object. So that'll look a lot like your lists. Thank you.
And in this book you have other markers that are
Great. So the way we're going to draw binary trees is by having a binary tree object that has two fields, a root node and a size field. And in the example I'll show you here, we'll have 7 nodes. And the schematic I'm going to use for these nodes is each node has 4 fields. There is a parent field and an item field. And so far this looks just like a SibTree node, but instead of having first child and next sibling, we're going to have every node having a left child, which we'll just call left, and a right child that we'll just call right. And so the root of our tree is a node with no parent. I'm going to draw an expression tree here that I drew in a previous lecture. So this is going to be an addition node, which is the sum of 2 different numbers. And one of those numbers is stored on the left child and one is stored in the right child. And the left child will be the root of its own tree, which will be a subtraction node. And that represents subtracting 6 minus 5. And we'll have another sub-expression over here where we divide 9 by 3. And those 4 nodes at the bottom are the leaf nodes. So they all have no left child and no right child. And every node is going to have a pointer to its parent. Except for the root node, which has no parent. So that's what a binary tree looks like to represent the expression 6 minus 5 plus 9 divided by 3. Any questions about that, how we represent a binary tree? So I want to remind you the definition of binary tree I gave you before. It's a tree in which every node has at most 2 children, and even if a node has only 1 child, that child is always either a left child or a right child. It's never neutral. We're going to use that property now to define a structure that has all of the properties of a hash table, has all of the properties of a binary heap, and additional powers of its own, but isn't quite as fast at doing those operations as specialized things like hash tables and binary heaps are. And they're called binary search trees. So the idea of a binary search tree is we want to implement... Oh, question over here. Did I do that wrong? Oh, yeah, I left out a pointer, didn't I? It does have 3 of its as its child. Sorry about that. A binary search tree is a particular data structure we're going to use to implement an abstract data type called an ordered dictionary. So we've already seen dictionaries, and one particular way to implement a dictionary is a hash table. An ordered dictionary is a little bit like a dictionary. It has all the same operations, but now we actually care about what order the keys come in. So just like a real dictionary puts the words in alphabetical order, our ordered dictionary will impose some sort of total ordering on the keys. Usually the keys are either numbers or they're strings, which we keep in alphabetical order. But we don't actually keep them fully sorted. We keep them sort of partly sorted, as you'll see. So an ordered dictionary is a dictionary in which the keys have a total order. Just like in a heap. But you can do things you cannot do with a hash table, or more generally with a dictionary abstract data type. You can quickly find the entry with the minimum or maximum key. So you remember one of the special powers of a binary heap is that it allows you to find the item with the minimum key. Well, this one will do the minimum or the maximum, but it's not as fast as a binary heap. But it is faster than just doing it with a list, usually. Or you can find the entry nearest another entry. So for instance, I can ask a question like, give me the smallest number that is bigger than 7 in this ordered dictionary. And you can do that kind of query relatively efficiently. So again, an ordered dictionary does everything a dictionary can do, plus these additional things. Finding minimum or maximum keys, find minimum key greater than something, maximum key less than something. Mm-hmm. Do we turn a leaf into a new node? Sometimes we do, yeah. Sometimes a leaf becomes an internal node. I'll show you all the operations soon, and you'll see how that happens. But we don't really have the concept of collision per se anymore. We have a different way of looking at things here. Now, a binary search tree is one of the simplest ways to implement an ordered dictionary. There are many ways to implement an ordered dictionary. A list would be the simplest one, but a binary search tree is a pretty simple one. So here's what a typical binary tree looks like. So we have a bunch of numbers, and they're arranged according to a particular principle, which is called the binary search tree invariant. So the binary search tree invariant says that if I have a node like 18 at the root of the tree, or at the root of one of the subtrees of the tree, then I'm going to put all the keys that are less than 18 in its left subtree, all the keys that are greater than 18 in the right subtree. And if there happens to be a key that's exactly equal to 18 in addition to the one that's stored in the root, that can go into either subtree. So, putting that all together, that means for any node of the tree, we'll call it X, every key in the left subtree of X is less than or equal to X's key. And symmetrically, every key in the right subtree is greater than or equal to X's key. So here again, if you look at 18, the left subtree contains numbers 1 through 15 in this case. I forgot a 17. Here we go. Let me add one more thing to this tree for later. So on the left side of the 18, we have a subtree with keys 1 through 17. And on the right-hand side, we have keys 25 through 30. Now, here's where it's really important that when a key has only one child, that child is a left child or a right child. So the 1 has a child, but only one child, which is the 3. And so the 3 needs to go on the right child of the 1, not the left child, because 3 is bigger than 1. And if you did have another 18 in this tree, like the root, then it could go into either the left or the right subtree. Doesn't matter which one. So I very briefly mentioned in-order traversals in a previous lecture on tree traversals. You'll recall that an in-order traversal is a recursively defined traversal that starts by visiting all the nodes in the left subtree, and then visiting 18 at the root, and then recursively visiting all the nodes in the right subtree. If you do an in-order traversal of a binary search tree, you will visit all of the numbers in sorted order. So with that tree, if you call in order on the root node, the 18, it will recurse to the left, recurse to the left, recurse to the left, and visit the 1 first, and then the 3, and then the 4, and so on. Any questions about that? Uh-huh. Not really. So a pre-order or a post-order traversal on this tree is just not very meaningful, usually. All right. What I'm going to do is make each item in each node of the tree be what's called an entry. And you might recall from the hash table lecture that an entry consists of two things: a key that we use to look up the entry, and a value, which is some additional information that we have associated with the key. So we're going to look at some hash table operations, and they're going to all return entries. So the first operation that we care about is the find operation. So we're going to pass in an object called k, which is the key, usually a number or a string, that we're going to use to look up an item in the tree. We want to find whether or not that particular key is in the binary search tree. And so here's the code to do it. I'm going to throw a public in front here. So we always start at the root, and then we start walking down the tree with a while loop that is going to keep going one step down, one step down, one step down, always going left or right until we either find what we're looking for or reach a null pointer, which means the thing we're looking for isn't there. So while the current node we're at is not null, we keep looking. We are going to need to do a comparison here. And I'm going to assume that all of the keys in this tree are comparables that have a compare to function. So I know this is a little long-winded, but this is essentially using the compare to function in the comparable interface to compare the key k that we're looking for with the key that's actually stored in this node. And that's going to return a number which is negative if k is smaller than this node's key, positive if k is bigger, 0 if they're equal. So if the key is smaller, that means we need to search down to the left child and see if the thing we're looking for is down there. And if k is bigger than what's in this node, then we search down to the right. But if neither of those two things happens, that means that the compare to function returns 0, which means the key we're looking for is the same as the key stored in this node. So in that case, we declare victory and we return the contents of the node. And then this closes off the while loop. And so from there, if the loop reaches the end, which means we've hit a null pointer walking down the tree, then we're done looking. We did not find what we were looking for, and so we can just return null or some other indicator that we did not find what we're looking for. Any questions about that code? So for instance, if this is my tree and I say, find 14, then I start at the top of the tree at the 18. I compare 14 with 18. 14 is less than 18, so I go to the left. I compare 14 with 12. 14 is bigger than 12, so I go to the right. Find the 15. 14 is smaller than 15, so I go left. 14 is bigger than 13, so I go right. Find the 14, return that entry. And that's how find works. So that one's pretty straightforward. What's a little bit more interesting is sometimes you want to find not quite the same key, or not a specific key. If you just want to find a specific key, a hash table is usually the most effective way to do it. But one thing that you can do with a binary search tree that you cannot do with a hash table is the following query. You want to find the smallest key greater than or equal to k, or the largest key less than or equal to k. And that's particularly interesting when k is not actually being stored in the tree at all. And so how do you do that? Well, you search for k as usual. And we notice something about a binary search tree, which is when you're searching downward through a tree, and you're looking for a key, call it k, that's not in the tree, then there are several other things we will encounter on the way down. We will encounter the node containing the smallest key that's greater than k. And we will encounter the node containing the largest key that's less than k. Both those things we will wander into. So as a demonstration of this, let's go back to the tree we started with, only this time let's see what happens if you do find 27. Well, if you do find 27, you start at the root at the 18. 27 is bigger than 18, so you go right. 27 is bigger than 25, so you go right. 27 is less than 30, so you go left. 27 is less than 28, so you wind up here. You wind up at a null pointer right there. And so the search for 27 has failed to find 27. But if you look at all the nodes we encountered on the way down, the smallest number greater than 27 is right here, and the biggest number less than 27 is right here. And so we did encounter both of them along the way. So if you want to implement a method that can find the greatest number that's less than k, or the smallest number bigger than k, then what you do is you take the code I just gave you for find 27 and you change it so that as it walks down from node to node, it always keeps track of the largest number it has seen so far that's less than 27, and the smallest number it's seen so far that's bigger than 27. And when you finally either find 27 or don't find 27 and hit a null pointer, then you have stored the answer to both of those questions. Yes? if you find 27, but it also has subtrees, then finding the smallest key that's strictly larger than 27 is a little bit trickier because you have to look both at all the ancestors of 27 and you have to look at the right child, the smallest key in that subtree. So it's trickier, but you can do it. It's not hard. Other questions? All right, so another method besides find that's pretty important is methods for finding the smallest or largest items in the tree. So Goodrich and Thomasia call these first and last. I think most implementations would call them min and max, but I'm going to stick with the Goodrich and Thomasia nomenclature for now. These are pretty easy to implement. And so, for instance, the first method, if the tree is empty, return null. And if it's not empty, otherwise you start at the root. You start at the root and you keep going left child, left child, left child, left child, until there's no more left child. And once you've hit a node with no left child, you're there. You're at the node with the minimum key. So that's the whole algorithm for finding the smallest key in the tree. And if we go back to our sample tree and see what that looks like, well, we start at the 18, the root node. We go to its left child, the 12. We go to its left child, the 4. We go to its left child, the 1. The 1 does not have a left child, so we have to stop there. And then we return the 1. Finding the max, obviously, is just the symmetric operation. You go to the right, you go to the right, you keep going to the right until you hit a node that doesn't have a right child, in this case, the 30, and that's the biggest number in the tree. You return that entry. Any questions about that? So now that we know how to find things, how do we change things? So the signature for the insert method for the binary search tree, it looks just like the signature for a hash table. You are inserting an entry that consists of a key, K, and an associated value, V, some information associated with that key. Could be a word and its definition, for instance. And it will return an entry object which contains both the key and the value. But it also inserts it into the tree. And the idea is that the insert method initially is going to look just like the find method because it follows the same path that find does. And this makes sense, because the reason why find works is because it follows the same path that insert follows. So we're going to walk down the tree as if we were doing a find operation, but we're not trying to find this key. We're trying to find a null pointer where we can insert that key. So when you reach a null reference, you replace that null reference with a new node. And that new node contains the entry we write this kv, the entry with key k and value v. And so, for instance, coming back to our favorite tree, if you insert 2, then, well, the parts of the tree that were already there don't change. But what you do is you start at the 18, you act as if you're searching for the 2. So go left to the 12, go left to the 4, go left to the 1. 2 is greater than 1, so now we're going to go right to the 3, and then go left to the, well, to the null pointer. So we have finally, by walking down the tree, reached a spot where there's a null pointer, and that's the right spot to add a new node with a 2 in it. And whatever associated value we passed in as v. Now, it may happen that I want to insert sometimes a node that's already in the tree, like, say, a 25. So if I wanted to insert a 25, I would start at the 18, I'd go to the right, and I'd find a 25. So now I've got a match. But it's okay to have more than one copy of the same key in a binary search tree. And when I hit a match, it's pretty much up to me whether I want to go to the left or to the right. You can do either one. Just pick one arbitrarily. So let's suppose we go left. There's another 25. Go left again. You can insert a 25 there. Any questions about the insert operation? Yeah. In the code that I gave you, yeah, the key does have to be an object of type comparable, or none of the code is going to work. You could change the signature of the method and say that k has to be comparable. I don't remember exactly why Goodrich and Tomasia didn't do that. Possibly to be consistent with the interface for the hash tables. Mm-hmm. You know, if you were to insert a lot of 25s into this tree, you would like to try to distribute them in as balanced a way as possible. So it would probably be a smart thing to do would be to like randomly distribute them. So every time you hit a key that's equal, you flip a coin, and if it's heads, you go left, and if it's tails, you go right. And that would give you a more balanced tree of 25s. Mm-hmm. Multiple 18s, the same rule applies, so not a problem. Oh, well, it would be difficult to retrieve all the 18s, but the binary search tree isn't really designed to help you retrieve all of them. It's designed to help you retrieve one of them. If you want all of them, you should probably consolidate them all into one node. So let's go to the hard operation. The most difficult operation to figure out with a binary search tree is removing a key from the tree. So you have you want to remove from the tree the entry with key k. Now this starts easily enough because when you want to remove something, the first thing you have to do is find it. So the remove operation starts out exactly doing the same thing the find operation does. Until you find it, nothing's going to change. Did you have a question? Just the first one that you find. Yeah, so this remove operation will just remove one copy, the first one it happens to find. Now, if you don't find it, then you obviously don't really do anything. So if return null if it's not in tree, just like find does. But if you do find one, if you do find a node with key k, then we got to figure out how to get rid of it. And how you do that depends on, once you find the node that contains that key, how many children does that node have? So if the node has no children, it's really easy. So if the node has no children, you just detach it from its parent. What that means is you set the parent's child pointer to null, and now that node is not part of the tree anymore. That's all you have to do. It's just a little bit trickier if n has one child. Then what happens is you essentially are moving the child of n up to take n's place. Like, for instance, if you had 5, 8, 2, and well, I guess that can't be 2, 4. If you had 5, 8, 4 like that, and you wanted to remove the 8, then the 4 just moves up to become the child of the 5. Like that. So that means you have to adjust the 5's right child pointer and the 4's parent pointer. And then the 8 is gone. But the hard case is when, well, question? Which one did... Oh, I'm still off, aren't I? Haha. Not my day. Yeah. All right. I think I got that right now. The hard case is when there's 2 children. When you're trying to remove a node with 2 children, that's a bit more painful. There you have to be a little bit more clever. So what we're going to do is we're going to look in one of n's children's subtrees. Specifically, we look in the right child of n, look at its subtree, and find the minimum key in that subtree. So once we've found this node x, we can remove x from the tree. And the reason why we can do that easily is since x is the smallest number in a subtree, it's the minimum in that subtree, it does not have a left child. So it's easy to remove something that only has at most one child. And once you've removed that, we're going to take the key that was in that node, and we're going to move it up and use it to replace the key that we're trying to get rid of. So we're going to replace n's entry with x's entry. Remember, n is the node with two children. We want to get rid of its key, but you can't really get rid of a node with two children. So what we do is we replace its key with a different key instead. So to show you what that looks like, let's come back to this tree. So the easy thing we could do is, for instance, suppose you want to remove 30. Then the 30 only has one child, so it's easy to just cross out the 30 and move this piece of subtree up to take its place. So now you have a 28 here and a 29 here. So again, removing something with just one child is easy. But suppose that you want to remove 12. So what happens? Well, we start at the top of the tree and we search for 12. There's 12. 12 has two children, so this is the hard case. So we're going to go down to its what did I do here? Here we go. Yeah. Okay, so we're going to go down to its right child, which is the 15, and we're going to look for the smallest key in the subtree rooted at 15. So remember, that's the minimum algorithm. The idea is you start at the 15, and then you keep going left until you can't go left anymore. So you go left to the 13. The 13 does not have a left child, so that 13 is the smallest key that's in the right subtree of 12. Now, since that 13 has only one child, because it has no left child, you can remove the 13 and move the 14 up to take its place. Then what we're going to do is we're going to put the 13 in the box where the 12 is, and that gets rid of the 12. So you'll notice now there's a 13 here in the box where the 12 is. We can't really get rid of a node that has two children, So instead, we just get rid of the key and replace it with a different key that we stole from further down the tree. And that's how you delete a key that has 2 children. Question? Move the largest key from the left? You mean, so why, are you asking, why do I take the smallest key of the right child instead of the largest key from the left subtree? You can do either one. They're symmetric. They're mirror images of each other. Either one works. We just have to pick one, so this is the one we pick. Yes? Yeah, so we are actually deleting a key value pair here. We're deleting the 12, and we're deleting the value that was associated with the 12. So we're deleting the whole entry. Mm-hmm. Yeah. If that 13 is 3, then that was not a valid binary search tree to begin with. So anything, the binary search tree invariant says that anything in 12's right subtree is greater than or equal to 12, so there can't be a 3 there. And that's why it works, is because you know that everything in that tree is going to be at least as big as 12. So the one thing that remains to talk about is just how fast do these things run. And the answer really is it depends. It depends on how perfectly balanced your binary tree is. Sometimes you're happy with that and sometimes you're not. So let's consider, for instance, if you get really lucky and you have a perfectly balanced binary tree, which doesn't happen very often, I should say. But if it's just perfectly balanced, and it has a height of h, then the number of nodes, call it n, is 2 to the power of h plus 1, all of that minus 1. And therefore, no node has depth greater than the base 2 logarithm of n. And if that happens, you're really happy. Now, the running times of find, insert, and remove are all proportional to the height of the tree. So if the height of the tree is log n, then so are the running times. To be precise, the running times are proportional to the depth of the last node you encounter. So, if you have a perfectly balanced tree, then all the operations run in order log n time on a balanced tree. But, sorry, you don't always get a balanced tree. Sometimes something, the opposite of that happens. For instance, suppose I take numbers that already happen to be sorted and insert them into a binary search tree. What happens? Well, I insert a 1, I insert a 2, I insert a 3, I insert a 4, I insert a 5, I insert a 6. I get a totally unbalanced binary search tree. Pretty much the worst thing you can do is fill in a binary search tree by inserting things that are already in order. And if you do that, then you have a depth of order n. And so I have to tell you that even though in an ideal world of perfectly balanced trees you'd have this great running time, a lot of the time you don't. And for all intents and purposes, and if you're asked on the exam, all operations on binary search trees have theta n worst case running time, where n is the number of items in the tree. And so that's the real answer. But we'd still like to dream about being able to always get log n performance. So on Wednesday, I will tell you how to keep search trees balanced so that you always do get log n performance. See you then.